Okay, good morning. So, actually, what we are supposed to cover for identities according to the book is done the previous session. But there are some formulas in the formula sheet. You always see them, but I decided actually to talk a little bit about them today, and then we go to the next lesson. Okay, so you can consider more or less this lesson an optional lesson, but I really recommend you to try to learn them. Okay, so an identity that I want to talk about today is so the identities we learned so far, if you remember, were a plus or minus b squared. So the answer is a squared plus or minus 2ab plus b squared. And we also learned that if I have a minus b multiplied by a plus b, this is the conjugate rule, it becomes a squared minus b squared. So mainly these are the only ones which you have to know about. But I also added two more in this list. Do you remember? We had a plus b plus c to the power of 2. So you might think that, okay, what happens? So here I have two terms squared. You might ask yourself, what happens if I have more terms squared? So that identity was an attempt to answer this question, and then we realized that this pattern can go on. So if you remember, what was this one? It was the first one squared plus the second one squared plus the third one squared plus 2 times the first one times the second one plus 2 times the first one times the third one, and finally plus 2 times the second one times the third one. I also added one more, and I call this the common term identity, or whatever you want to call it. Why this is called so? Because I want to multiply two binomials. Binomial means a polynomial containing exactly two terms. So that's a binomial, that's another binomial. I want to multiply them, but they have something in common, and that term is x. So the answer to this was the common term squared, the sum of uncommon terms multiplied by the common term, and then the product of uncommon terms. So I added these two to the list of identities that you have to know. These are not, of course, in the formula sheet. But there are two more that I want to add. There are some more that I want to add today. So one thing is the extension of this. Here, one possible of generalizing this rule was what happens if I had more terms to my expression, and still I want to square it. Another question is that what happens if I have the same two terms, but if I want to raise it to higher powers? Okay, so one more, I will discuss it today, but if you take the Math 5 course, we will answer that question for a generic n. So if a plus b to power 100, we find a formula for calculating that one, expanding that one. That is called the Newton's binomial theorem. But for the time being, let me just increase the exponent just 1 unit. This, what I write here, you always have it in the formula sheet, but usually you don't use it. And that is this. If I have a plus b to the power of 3 rather than 2, the answer is this. So this becomes a to power 3 plus 3a squared b. So the first one cubed plus the 3 times the first one squared multiplied by the second one, plus the other way around, 3 times the second one squared multiplied by the first one, and finally plus the second one cubed. And using this identity, it is better to interpret the first one and the second one with the terms containing the signs, okay? So that is, first of all, if I introduce an identity, I have to have a proof for it for you. So if I want to prove an identity, I start, for example, from the left-hand side and try to do some algebra and reach to the other side. So the left-hand side is this expression to power 3. But expression to power 3 means the expression to power 2 multiplied by that expression. Or if you don't mind, let me put 2 here. It doesn't matter, of course. So this is the left-hand side. But for this one, I can use this identity. So this becomes a plus b. and then it becomes a squared plus 2ab plus b squared. Of course, I could have written 3 times of them and multiplied them, but because this is the lesson for identities, I want you to develop this habit so that you can use identities as much as possible when applicable. So here, what I do, there is no particular identity involved, so I have to start multiplying things. So then a times a squared, a cubed, I just continue multiplying that, yes? And then I go to this term. And then finally b cubed. And then I realize this one and that one are similar. These two terms are also similar. So if I combine them, I will get the answer. Yeah, so this becomes a to the 3 plus 3a squared b plus 3ab squared. And then finally plus b cubed. And that's the right hand side. I recommend you to learn that. Yes. It's a good identity. What happens if I have negative sign in between? That's what I'm saying. If you want to memorize, it's enough. You don't need to memorize 1 for minus 1. So if I want to calculate what is a minus b to power 3, then what I can interpret this, I can interpret any difference as a sum. Yes, I can imagine that a minus b means a plus minus b, and then to the power of 3. Okay, then I will follow the same rule. So this tells me the first one cubed, which becomes a to the 3 times the first one squared, multiplied by the second one, but the second one is minus b, plus 3 times the second one squared, multiplied by the first one, and then plus the second one cubed. But then let us see what happens. This becomes a to the power of 3. This is positive, this is negative, multiplied, so it becomes negative. So this will change the sign. This sign is changed from the original version. But this sign is not changed, because even though it's minus, but I'm raising it to power 2, so it becomes positive b squared again. And then when I multiply it here, it becomes 3ab squared. So positive, negative, positive, and the next one becomes again negative, because minus b to power 3 is odd, so it becomes minus b cubed. So this is why I'm saying that you really don't need to memorize something else for the negative sign. You can immediately find it from the positive sign version. Yes, is that clear? Okay, because I told you that you see this formula in the formula sheet all the time, but yeah, I don't know if this is in the curriculum. If you have it in the formula sheet, you should have it somewhere in your lessons, but I don't see them. Anyway, so this is one thing that I want to mention. Let me give you an example. Yeah, we can, for example, just let us calculate this. Let's expand this. I want to write 2x minus 3y to the power of 3. Can I use this identity? I would say yes, because I have a binomial and I want to raise it to power 3. Whenever I need to do this, I can use that. Okay, so what can I do? I would say the first one to power 3, the first one cubed, plus 3 times the first one squared, multiplied by the second one. So I told you that in this, it's better to use the second one with the sign, containing the sign. So this becomes 3 times the second one squared, multiplied by the first one itself, and finally the second one cubed. Okay, so this becomes 8x cubed, and then let us do that in our head. 2 to power 2, 4, times 3, 12, times minus 3, minus 36. And then I have x squared y. And here, minus 3 to power 2, positive 9. Positive 9 times 2 is positive 18. Positive 18 times 3, positive 54. And then this one to power 3 is negative. 3 to power 3 is 27. And y to power 3. But you need to make sure that you cannot simplify more now. So this is the end of the story. So when you expand this, you will get this. Yes? Because these are optional ones, I don't want to go very deep into them. Just one example is enough. Is that clear? Okay. There are two other formulas that appear in the formula sheet almost all the time, and I think they are good formulas to know. It's a little bit, you need to understand what is going on. I will write two versions for it. So what happens if I have a okay. So what you need to remember this combination. So a plus b. Oh, it's making trouble for us now. Let's hope that it will work. Okay, so I have this a plus b, and then I have okay, hopefully this will work with this microphone now, but I have to speak a little bit louder. Okay, so this is the identity that I want to talk about. You have a plus b with a little bit of strange combination coming after that. So you have a binomial multiplied by a trinomial, but not any trinomial. A trinomial which is connected to your binomial in this very particular way. So you have the first one squared, you have the second one squared, but you have the product of these two terms in the middle with the opposite sign. Okay? So this combination appears in a lot in mathematics. Okay, so this is why they talk about this identity. So what you have a binomial multiplied by a trinomial, but not any trinomial. A trinomial which is constructed from the binomial in this very particular way. You have the complete squares of these two, you have the squares of these two involved, you have the product of these two involved with the opposite sign. If that is the case, answer to this is the first one cubed plus the second one cubed. And again, I can have a binomial with the negative sign in the middle multiplied by trinomial, but not any trinomial, the trinomial which is constructed from my binomial in the same particular way. Meaning that I have this squared, I have this squared, I have the product of them, but with the opposite sign. So if it's negative, it's positive. So if this combination is exactly like this, then you can write a cubed minus b cubed. So these two formulas you always see in the formula sheet. But let us just introduce them. That's it. If you want, you can use it in the exam, but it is not compulsory. I will not design questions in a way that you have to use. Okay, again, when I introduce an identity, the first thing that I should do is to prove it for you. Okay, let us just prove one of them. For example, I can take the second one. It doesn't matter. So the left-hand side of the second one is this one multiplied by that. There is no identity. I have to expand. So a times a squared becomes a cubed. A times ab, a squared b, and a times b squared. And then you have minus ba squared. And then you have minus ab squared minus b cubed. I just multiplied them. That's it. And then all of a sudden, this is engineered in that way. So you see that the middle terms are all cancelled. So this a squared b is cancelled with this negative sign. This is also cancelled with that one. That is the reason you see this cancellation happens. And then you see that this becomes a cubed minus b cubed. And that's exactly equal to the right hand side. So to be honest, the reason that I brought this up is because for the next lesson, if you want to factorize, using conjugate rule, you can factorize the difference of complete squares. What is the factorization? Do you remember? Means I give you an expression, you are supposed to write it as a product. So if I give you a squared minus b squared using the conjugate rule in the reverse order, you can factorize it. But now this will help you in the future. If I give you the difference of cubes, of two complete cubes, or the sum of two complete cubes, and I ask you to factorize that, you can use these identities to factorize this. Okay? So that is the main reason people are interested, because they are interested in factorizing things. And the sum of cubes and the difference of cubes appear a lot of in many places in mathematics. So it is good to know how to factorize them. Okay. For example, I don't know. Let me just write one example here. I told you, because these are optionals, I will not go very deep into them. So, for example, I have 2a minus 5 multiplied by 4a squared plus 10a plus 25. Of course, if I give you this, you're supposed to expand it. If you cannot detect what the pattern is, you can just simply multiply it, because I told you this algebraic identity is optional. But can you see the pattern now? First of all, you see a binomial which is multiplied by a trinomial. So you need to get suspicious about that might be these identities are useful. But you cannot use them blindly until you realize that the pattern is exactly the same thing. So here I have my binomial. I have total freedom here. I have complete freedom here how to choose my binomial. But choosing my trinomial, I do not have any freedoms at all. It has to be engineered in a particular way for my polynomial. I should have the first one squared. I have it. I should have the second one squared. I have it. I should have the product of these two with the opposite sign, and I have it, because the product of these two is 10a. With the opposite sign, I have positive 10a. So that's exactly according to which pattern? To the second pattern. So the answer is the first one cubed minus the second one cubed. But 2a cubed is 8a to the power of 3, and 5 to the power of 3 is 120. Yes? So that is an idea how can you use this identity. Okay. I don't want to give you more identities. These are, I think, enough. So I would say that 1, 2, and 3, and 4, more or less. So we have 4 new identities. Some of them are actually useful in the future lessons. Okay, so today I want to spend a little bit of time to solve a little bit of diversity of problems related to identities together, so that we can start tomorrow with the next lesson, which is factorization. Okay, so let me just give you some examples. I want to mainly give you these examples, let you to think, and then come back and solve it together. Okay. So first of all, let me ask you to calculate these numbers. So example, evaluate each item. So number 1, we have 235 squared minus 230 squared minus 5 squared. I'm not asking you not to use the calculator, but of course putting this in the calculator is super simple, okay? Yeah, try not to use the calculator if possible. That is probably a good way. Number 2, 850 squared minus 750 squared. Number 3, 497 multiplied by 503. And finally 4, 99 to power 3. Okay, so I give you a little bit of time, not that much, it's not hard. The ideas are clear. Okay, so let us see how it goes. So what is your suggestion for the first one? Yes? Do you have any ideas how to do the first one?
Use conjugate rule.
Conjugate rule is helping. Because the difference between them and then multiplied by the sum of them, the difference between them is quite good. It's 5. But
The last two, right?
yeah, I was thinking that because this is 230 and that is 5, if you add them together, it becomes 235. So might be the squaring rule is probably better here, because then I can immediately get rid of these two. How? I can write the first one, 230 plus 5 squared. And then I just write them down. So it's minus 230. I mean, the reason they have written 5 to power 2 probably are helping you to understand this pattern. I'm not sure. Let us see. Then according to the rule, it becomes the first one squared, 230 to power 2. 2 times the first one times the second one, which is 2 times 230 times 5. And then plus the second one squared, which is 5 to the power of 2. So what I have written so far is the expansion of that part, but then after that I have this and I have that, so it becomes minus 230 squared minus 5 squared, and I think it's much simpler, yes? Because what happens, this one is the big one, it's gone, and here I also have this small one gone, and this is left for me. But this is also easy to calculate, because rather than multiplying this and then by 5, I multiply 2 by 5 first, it becomes 10, and then multiply 10 here, so the answer is just simply 2,300. Yes? What is the second one? The second one is clear. So I have to use the conjugate rule, but in the opposite direction. I mean that I'm factorizing it, to be honest. So what should I do? I would write 850 minus 750 multiplied by 850 plus 750. But this is very simple in that case, so that is 100. This is how much? What? Sorry. It is, sorry. It's, yes, that's correct. 1600, yes? Am I right? Yes. And then of course this is super simple to multiply. This becomes this. 160,000. Okay? What is your opinion about the third one? Is there any rule that I can use? Conjugate rule again, but the focus is on 500, yes? So this one is 500 minus 3. This one is 500 plus 3. So then it becomes 500 minus 3. And then I have 500 plus 3. And the answer becomes the first one squared minus the second one squared. The first one squared is simple with 4 zeros, yes? And then I have minus 9. So what's the answer here now? What's the answer? It's harder to calculate this one rather than
249,991.
So just you told me I was 2,000? Yeah, it's
4,991.
So that's the answer. But this is somehow optional. This is the one that I just told you today. So because you have cubic, you have the 99 to the power of 3, so what should I write? 100 minus 1 to the power of 3 is a good choice, yes? I would write it as 100 minus 1 to the power of 3. According to the rule of power 3, it becomes the first one cubed plus 3 times the first one squared multiplied by the second one plus 3 times the first one multiplied by the second one squared, and then finally what do you have? The second one cubed. But then this becomes 1 with 6 zeros. And then here it becomes minus, this is 10,000. And this is 1, so this is 300. And then I have minus 1. Okay, so what the answer to this one is? That's up to you to calculate. Yes. But I mean, it's not that hard. So it is 1,030,000 less.
299.
What?
1
This
million.
is 1 million
Yeah,
minus
1 million.
30,000.
Sorry,
Yeah.
900.
Yeah. And then you just do this yourself. Okay. I'm not finishing with that. Okay. Let us just go to the other exercise. Okay, a little bit more interesting problem. Let us just do this. I give you this example. If a is a square root of 2 and b is a square root of 2 minus 1, what is this expression? A plus b multiplied by a squared plus b squared multiplied by a to the 4th plus b to the 4th and then plus b to the power of 8. So this is a better question. So I have given you two. The problem is essentially is very simple. If you have calculator available, so for example, using GeoGebra, you write this expression, you substitute this number for A in that expression, you substitute this number for B in that, and then ask GeoGebra to calculate. So I mean, in principle, this is a very simple problem. But I want you to understand how you can calculate it effectively with hand, without any digital tool. So I want to wait a little bit for you. Can you see that? How can I calculate that expression? Okay, because I want to finish this lesson today, let us just start doing things together. Okay, do you have any idea for that problem there? No ideas? Okay, so I will teach you the trick. So here, this question mark is equal to, let me just rewrite it in front of your eyes. So this is a plus b, and then I have a squared plus b squared. Then I have a to the 4th plus b to the 4th. And then I have plus b to the power of 8. Okay? I will give you the hint, but you can tell me why this hint will actually is effective. So what I write, I put a fraction line here, and then I put plus b8 there. So I copy and paste this part, no worries. But here, I start from a minus b. And then I would write a plus b, a squared plus b squared, a to the 4th plus b to the 4th. And then of course, I cannot change the problem. I have started with this one. I just divide to compensate for that. So I hope that you agree what I have written here is still the question mark. Yes?
Yeah, now it's just conjugate rule.
Yeah, all over again. Yes? No, but first of all, everyone agrees that what I have written is valid here. Yes? So what I did, I multiplied by a minus 1, a minus b, and also simultaneously divide by a minus b to compensate for that change. So this means nothing has changed. But why this might be useful? The reason is that these consecutive conjugate rules appear. So because these two, you realize that's a conjugate pattern. So this becomes a squared minus b squared. But then it is engineered actually in this way. So the answer from these two makes a conjugate pattern for the next one. And then if you multiply that, what is the answer then? So if you want, I can write it down, but it's too boring, but you'll understand what is now. This one multiplied by that one, what's the answer? The first one to the 2, which becomes 4, minus the second one to the 2. And then you realize this one with that one is also a conjugate rule. So let me just write the answer now. So what will happen? The denominator is still a minus b, but the numerator is what is the numerator now? This one multiplied by that is 8 to the power of 8 minus b to power 8, and then I have plus b to power 8. Yes? So you might think that still the problem is not solved because still raising this number to power 8 is not hard. By the way, can you tell me what is this number to power 8?
16.
It's a square root of 2 to the power of 8, means 2 to the power of 4, which is 16. But calculating this one to power 8 is actually hard. Why is that? Because square root of 2 minus 8 is a binomial. You have to write this to the power of 8. Of course, you can use identities, but not very straightforward. You need to raise the power little by little. But that is not a big problem because they have engineered these numbers so that this is very simple. What is a minus b in this particular problem? 1. A minus b in this problem is the square root of 2 minus the square root of 2 minus 1. So this becomes the square root of 2 minus the square root of 2 plus 1. That's gone. So actually in this particular case, the denominator is 1. Yes? And the denominator is 1, I don't write it, but then the nice thing is that this is minus b8, and that's positive b8. They cancel out. So this means that this is exactly equal to a to power 8. Because this expression for these numbers is equal to 1. Okay, and then that is exactly the answer. So this becomes now square root of 2 to the power of 8 means 2 to the power of 1/2 to the power of 8, which is 2 to the power of 4, which is 60. So the answer to this problem is 60. Is that clear? Okay. But I just want you to see there might be some interesting and nice problems going on. But let us come to this exercise, which is actually important, I think, of course, I have also included the optional identities. Let us see how it goes. Here, you want to expand this. What is your opinion? I am asking you to use identities as much as possible. Of course, if you don't want, you can just expand by simply multiplying and simplifying at the end. But the whole goal of this exercise is to train your eyes to catch these patterns as soon as possible. So do you see that there is any identity involved here? A minus b plus c, a plus b minus c. So let me write here on this board. At least you should have some idea if one of these identities is useful. Which one is it? For this problem, conjugate, yes? But of course, it is not exactly according to the conjugate pattern yet. You have to change the form of it slightly so that the conjugate pattern emerges. Yes? So for example, number 1, what can I write? For the first one, I can factor a negative sign out and I write it like this. Do you agree? Because what I have written here, so instead of the first factor, I took this minus sign out and I wrote it in that way. Do you agree? Because if I put the minus sign back, this becomes minus b, this becomes positive b. So it is completely valid. Instead of this, I write it. Yes? But in the second one, I just write the same thing, but make it clear, I would put a pair of brackets around b minus c. It is not necessary. The reason that I put it like this, because I want you to see the pattern. A plus b minus c, a plus b minus c. So I haven't changed anything. But now you see that conjugate pattern emerges, yes? So this becomes the first one squared minus the second one squared. But you want to expand, so you have to get rid of all pairs of brackets. So this means that now this is the squaring rule. So what you need to do, you need to write a squared minus, you expand this expression, b squared minus 2bc and then plus c squared. And then you will have to get rid of that pair of brackets by opening it up. So this becomes minus b squared. The second one becomes positive 2bc. And the last one becomes minus c squared. So this is what you need to write for the first. Okay. For the second one, I think that's also somehow clear, at least the first part. Do you see any kind of pattern in this product? The first two actually form a conjugate pattern, yes? So number 2, I can write it as, which one is the first one here? Is 1 the first one or 2a? 2a is the first one, because I told you when you want to see which one is the first, which one is the second, the one with the sum is not sensitive to the order. This is sensitive. So the first one is 2a. So the product of these two, I can write it as 2a to the power of 2 minus 1 to the power of 2. So what you see that I have written here is the product of these two, and I copy and paste this part. So this is 4a squared plus 3. But then what happens? This becomes 4a squared minus 1, and then you have 4a squared plus 3. Of course, in this case, if this is in the exam, there is no identities. Here you can just multiply. But can you recognize which identity is that? One of the optional ones. So I have binomial multiplied by another binomial, but there is something in common, and that is 4a squared. So do you remember what was that? The answer was the common term squared. We can do it in our head. That's the only reason that we learned that identity, to do things faster. So this one squared is 16a to the 4. And then you remember the sum of non-common ones, 3 and minus 1. If you add them, it becomes 2, and then multiplied by the common term, which becomes 8a squared. And finally, the product of non-common terms, which is minus. Yes? So that's it. Number 3. Do you have any idea what to do? Yes, it is common term here. But I would say, yeah, that's common term only. Is there anything better we can do? No. Okay. Well, so we use the common term for the first two. Yes? So let us just do it in our head. The common term squared, which is 4a squared, the sum of non-common terms in your head, minus 5 minus 1 added is minus 6, and then multiplied by the common term, minus 12a. And then the product of non-common terms, which is positive 5. And then you have to copy and paste the rest of it. So it is 4a squared plus 12a minus 5. Now again the question is, can you recognize a pattern again? It's a conjugate rule, but you have to engineer it a little bit. Yes? So this is a conjugate pattern. So why? Because I can write the first one in this form. I take a minus sign out. Yes? Minus plus. That's the same thing. And then I can write it as 4a squared. I just put a pair of brackets, even though not necessary. I just want to make things clear for you. And then you can immediately see that's a conjugate pattern again. So the answer is the first one squared, which is 16a to the 4, and minus the second one squared. Yes? But what you need to do again, you have to use a squaring pattern here. So this becomes 16a to the 4th, and then minus. The first one squared is 144a squared. 2 times the first one times the second one is minus 120. Yes. A. And then the second one is plus 25. But then of course you have to open it up. So this means that this becomes 16a to the 4th minus 144a to the 2 plus 120a minus 25. Yes? Okay, so that was number 3. What about number 4? Do you have any idea what to do? Yes, some might be you are tempted to actually, that is not wrong. This is a conjugate pattern, I agree. You can also assume this is a conjugate pattern. Yes? And then you have to work it out. But I think it's a better way. Yes, Sergey?
The second one and the fourth one.
Yes, this is one of these. Yes, so that's the trick. If you fall into this trap that you use conjugate rule, it will work eventually, of course. But I think it would be more tedious. You can check that out yourself. The best thing is to take the first one with which one of them? It's on the board. You need, if it's negative, to make the right trinomial, this should be positive. So the first one and the third one, the second one and the fourth one. Yes? So if you don't mind, let me just write in front of it. So this becomes what? I will take this one and that one. I will take this one and that one. Because, am I allowed, by the way, to do this? Yes, because I am multiplying four numbers. It doesn't matter in which order I multiply and in which order, in which collection I collect them to multiply. So this one and that one. It's much simpler. So what is the answer? This by that, the answer is the cube of the first one minus the cube of the second one. And then this one by that one is what? A to the power of 3 plus b to the power of 3. But of course, pairs of brackets are left. It's not finished. But again, that's a conjugate pattern revealing itself. Yes? So then becomes what? The first one to the 2 is minus the second one to the 2. So the answer is so simple. So you see that sometimes it is effective if, of course, the exactly the right combination appears. Okay, do you have any idea what to do here?
If you split the squared up, and then you make conjugate patterns.
Yeah, exactly. Because, so if you have a to power 2, b to power 2, c to power 2, you can write a, b, c totally to power 2. Yes? So that's the idea. So what we can write the power of 2 here, and then I can write 2a minus 1, 2a plus 1, and then I have 4a squared plus 2, yes? But then again, this is a conjugate pattern. So what I can write the first one to the 2 minus the second one to the 2, that's it, multiplied by this one, and then raise it to power 2. Okay, but this, what identity is this one? Is the common term identity. Let us just do it in our head. So I have this pair of brackets, and then I have a second power here. The common term squared is 16a to the 4. And then the sum of these non-common ones, which is 1, multiplied by the common term, which is 4a squared. And then multiplication of the non-common terms, which is minus 2. But the problem is not finished because I have to get rid of pairs of brackets, which identity is that it's a trinomial and I want to square it. So what can I do? It becomes the first one to the 2, 256, 8 to the 8. The second one to the 2, 16, 8 to the 4. The third one to the 2 is 4. 2 times the first one times the second one is 128, a to the 6. Am I right? Yes. 2 times the first one times the third one, which becomes negative 64, a to the power of 4. And finally, 2 times the second one times the third one, minus 16, a squared. Is the problem finished? No, because there appear actually one similar term. So we have to calculate them, then it is finished. So 256 a to the power of 8. This one minus that one minus 40. So let me write them in order. It doesn't matter, of course. So let me write this one 28 a to the 6. And then I go here minus 48 a to the 4. And then I have minus 16a squared plus 4. Yes? Okay, we can do these two quickly as well. Yeah, there are 3 left. So what is your opinion? Of course, we will have an identity if you study Math 5 for this directly, but here we don't have power of 6 as our identity. So what do you suggest here?
So yeah, it's all.
Of course, this is not a very actually good exercise. This is a brute force calculation. I don't think there is something we can do. Of course, we can use power of 2 and power of 3, but for power of 2, I told you the pattern will continue. So so if you want to do it, a1 to the power of 6, you can interpret it in 2 different ways. Which one is more efficient for our case, do you think? I can interpret it as a minus 1 to power 2 to power 3, which is right. I can interpret it as a minus 1 to power 3 first to power 2 second. Yes? If you want to go, actually this is a lengthy, boring calculation at the end. There's nothing interesting in it. But if you want to start this boring calculation, which one will be your preference? So this one of the... If you want to use the first one, I would prefer the second one. Because the first one gives me a trinomial, and the trinomial to power 3, I don't have any particular pattern in mind for that. But this will give me it gives me 4 terms, but 4 terms to power 2 more or less follows the same rule as the 3 terms to power 2. I told you that time. So I would prefer to do this. So this one becomes the first one cubed, minus the 3 times the first one squared times the second one, 3 times the first one second the power of 2, and then the second one to power 3. That is the expansion of the first one. And then I have the second power of 2. But this is not 3 terms, this is 4 terms. But for the 4 terms, the pattern is exactly the same. I just mentioned it briefly last time when I was talking. I didn't prove it for you, but that pattern is also going on. So the answer becomes the first one cubed, the second one cubed, the other one cubed, and then plus 1. But 2 times the first one times the second one, 2 times the first one times the third one, 2 times the first one times the last one. But then I go here, 2 times the second one times the third one, 2 times the second one times the third one, and then 2 times finally this one multiplied by that. So I would say that this is easier. If I have started with this one, then I have a trinomial which I have to raise it to power 3. But for power of 3, the pattern is not that simple. I don't continue this. This is not finished. You need to find a similar ones. For example, this one and that one are similar. This one, I don't know, with that one are also similar. These 2 are also similar. You combine these similar ones, and then you have your answer. Of course, in Math 5, as I told you, we will find a formula that you can expand this directly without having to go through these 2 steps. Okay, there are 2 more left. I think these are not hard. So what do you suggest for number 7? A minus b to power 3 times a plus b to power 3. Of course, there is one option to expand this using this identity, expand this and then try to multiply, which is heavy calculation because 4 terms times 4 to 16 terms. Yes?
And we can write them in one.
Yes, so that is the best way to do it. So number 7, this becomes equal to, as you said, a minus b and then a plus b totally to power 3. And then this becomes conjugate rule, so this becomes a squared minus b squared to power 3. Then we have the rules for the third power. So this becomes the first one to power 3, which is a6, 3 times the first one squared times the second one, which becomes what? Minus 3a to the 4 b to the 2. The other one becomes 3a to the 2 b to the 4. And finally, the second one to power 3 minus b to the power of 6. So we were able to, of course, this is a little bit artificial problems you see here. They have engineered these combinations so that it is easy to expand. But the goal of this exercise is to train your eyes to catch the patterns if possible. Yes? Okay, this is also interesting, I would say. So do you have any idea how to start this? I mean, there is no probably a unique way to do it, but I think I see how they have engineered the problem. That's the whole point. If I can catch the pattern after exercising and repeating things, you should also be able to catch the pattern. Yes, that's the whole exercise. It's a really artificial problem, yes? They have just managed it. They have written something because they had something go. If I am able to read their mind because of experience, by exercise you should also be able to read their mind, yes? That's the point. So do you know how they have done it? So that you can expand it a little bit more efficiently. And I just want you to know that these problems are not hard problems or deep problems. At the end, if you are patient, you start multiplying them, expanding them, you are done. But the point is to be able to do it faster and more efficient. That is the whole goal of this exercise. Yes? So for example, the guide is to look at this term, x squared plus 9x, and then go back and see what this is telling you about how to do this part. If I just give you the first two, what is the name? The name is the common, I don't know, whatever it is, common term identity. Okay? So you can take this one with that one, common term. You can take this one with that one, common term. You can take this one with that one, common term. I don't know which combination is good. This is hinting you. Yes? The first one and the last one. Why? Because you have the sum of non-common terms multiplied by the common term, and this 3 plus 6 gives you 9. And exactly 4 plus 5 also gives you 9. So that is the reason, okay? So, I mean, if I want to solve that one, let me write it patiently. I would write the first one next to the last one, or I would say the last one next to the second one, and then I will keep the order as it is for the other two. Let me just copy and paste everything for the time being, except that I just reordered them, okay? And then minus x squared plus 9x, and then to the power of 2 minus 360. Okay, this is the common term identity. So this becomes the common term squared, the sum of non-common terms multiplied by the common term, and then multiplication of these non-common ones, which is 80. Yes? I do the same thing here. It is the common term squared plus, what happens? The sum of these two, which is 9, multiplied by that, again 9x. The product of these two is 20. And then I have minus x squared plus 9x to the power of 2, minus 360. Now, can you see what happens? What is your suggestion for expanding the first one? Do you see that the first one is also a common term identity? But the common term is this guy. Yes, that's a common term identity, but the common term is this guy. So this becomes the common term squared. And then the sum of these non-common ones, which is 38, multiplied by the common one. plus the product of non-common terms, which is 360, and then everything. And now hopefully you realize you really don't need to expand that because this is gone, yes? So that's the whole point. I mean that by training, you can actually read the mind of those people who actually did this. It's not hard. So you see now, whatever this guy is, I don't care, just because this is cancelled with that one. And this one is also cancelled with that one. Yes? And then what we are supposed to do, we just need to expand that. So this becomes 38 x squared. And then you have to multiply is 2, 7 goes there, 27, 34, I think, if I am wrong. This becomes this. Am I right or not? Yeah. So that is also the whole point. So I think it's good to train yourself to use identities if possible. Because in the future, when you are supposed to, so for assume that you are working on a project and you are supposed to simplify an expression, you really don't know is there any identities involved in the problem. So this is why I'm saying that if you want to do your calculations more effectively, it's good to train yourself to catch these patterns, to be able to do things efficiently. But I told you at the end, there is nothing deep about these things. We are just expanding them. And usually it's not that colorful these days because computers can take over these boring calculations. And we don't care about actually to catch the patterns because we just type this in the computer and the computer will actually give me this answer. So it is probably, yeah, it's just a brain exercise if you want to, yes. But other than that, there is nothing very deep here. So what is the goal? The goal is just to expand, writing an expression in the most simplified expanded version. Expanded means no pairs of brackets to left. The other one is actually more important, the other method. So the other lesson, the next lesson is actually factorizing, but that is really important. So for example, if you want to calculate the derivative of some functions, you have to calculate the limit, and in the limit you have a fraction. So in principle, you should be able to simplify those fractions, yes? So that is, the next lesson is more important. But you don't understand the next lesson unless you have a good grasp of what is going on by expansions and things like that. Yes? Any questions? Okay, thank you. I don't know, I will check that if the video audio quality is good, I will publish it. Otherwise, we just need to forego it. Thank you.